Hi. The first topic in the chemistry syllabus for common university entrance test is solid state. Some of you may not have studied solid state in class 12, but you need not worry. I am uploading video classes on the prescribed topics in 3 parts, which include a lot of previous year multiple choice questions and other model questions for CUET UG. By the way, I am Dr. Suriak Matthew, a retired professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes on topics in chemistry related to NEET, JEE Main and Advanced, CUET, and other similar examinations. If you like the video, please subscribe my channel and forward to others. In solid state part 1, we learn about the characteristics of crystalline solids, different types of solids, and a close packing in solids. The solid state embraces the wide varieties of steel, the semiconductors and the metallic conductors, the ceramics, and other materials used in the fabrication of many of the common objects in the modern world. The properties of solid arise from the arrangement and properties of the constituent particles, which may be atoms, ions, or molecules. The other two states of matter, liquid and gases, are called fluids because of their ability to flow. The fluidity in these states is due to the freedom of movement of the constituent particles, say molecules. But in solids, the constituent particles have fixed position and can only oscillate about their mean position. The three states of matter. Of course, a fourth state of matter also exists, the plasma state. It occurs at high temperatures and contains ionized substances. Here we consider only the other three states, the gas, liquid, and solid. Gases are characterized by low density, high compressibility, and the ability to expand and fill the available space. The intermolecular forces are negligible. The gas particles have high kinetic energy. Liquids have a definite volume but no fixed shape. It takes the shape of the containing vessel. The intermolecular forces are stronger than gases. Liquids are characterized by properties like fluidity, density, viscosity, surface tension, vapor pressure, etc. Solids have definite shape and volume, high density, and are highly incompressible. The intermolecular forces are strong and it keeps their constituent particle in fixed positions. And they can only oscillate about some mean positions. Here we mainly consider the crystalline solids. The general characteristics of solids are the following. Have definite mass, volume and shape. Intermolecular distances are short. Intermolecular forces are strong. The constituent particles are fixed positions and can only vibrate about some mean position. Incompressible and rigid. Solids are broadly classified as either crystalline solids or amorphous solids. Sodium chloride is a crystalline solid. This is the crystalline structure. The green balls represent chloride ions and the small balls represent sodium ions. This is quartz, that also is crystalline. On the other hand, carbon black as well as a glass sheet, these are amorphous solids. Let us study some of the characteristics that distinguish between crystalline and amorphous solid. One is the arrangement of constituents. Crystalline solids have long-range order. Long-range order means the regular pattern of arrangement of particles repeat itself periodically over the entire crystal. On the other hand, amorphous substances have short-range order. Short-range order means the ordered arrangements are limited to some regions only. Quartz is made up of SiO4 tetrahedra. Here we can see the perfectly ordered arrangement. And such an arrangement is called the long-range order. But when we come to quartz glass, so this is quartz glass which is amorphous, and the ordered arrangement can be seen only in some places. Quartz is made up of SiO4 tetrahedra. We see here the bottom part of the tetrahedra. So these white balls are the silicon atoms, and the red are oxygen atoms, and one oxygen atom is towards the other side. And this is a three-dimensional structure. Another property that distinguishes the two categories of solids is the melting behavior. Let me take some crystalline solid in a test tube, and I am heating it on a Bunsen burner. Suppose the temperature has reached 110 degrees, and I am continuing heating, and the temperature gradually increases to 111, 112, and when the temperature has reached 112, suddenly all the crystalline substances are converted to liquid state. And such a melting is known as a sharp melting. Now I take a small plastic piece in a test tube, and I am heating it. Suppose the temperature has reached 81 degrees. And at 82, the plastic piece slightly shrink, and at 83 it again shrinks, and suppose at 84 it is converted to a liquid state. So it melts over a range of temperature. And in the case of crystalline solid, it has a sharp melting point. But the amorphous substance, plastic is an amorphous substance, and it melts over a range of temperature. Crystalline substances possess a regular ordered arrangement of constituents. Consequently, they have uniform intermolecular forces, and these forces break uniformly. Hence shows a well-defined sharp melting temperature. On the other hand, in an amorphous solid, the constituents are irregularly arranged. So intermolecular forces among them vary in strength within the sample. Melting occurs at different temperatures for various portions of the same sample as the intermolecular forces are overcome. Another property that distinguishes these two types of solids is the cleavage property. When cut with a sharp-edged tool, the crystalline solids break up into two pieces with smooth surfaces. So the surface is very smooth. Now, if you cut an amorphous substance in a similar way, it breaks into pieces with irregular surfaces, like this. So this is crystalline solid, and this one is amorphous solid. The cleavage or shattering of a crystalline solid produces fragments having the same or related interfacial angles and structural characteristics as the original sample. Solids with irregular structures such as glasses shatter irregularly to yield pieces with curved edges and irregular angles. Crystalline solids are anisotropic. Anisotropic means not the same throughout, and isotropic means same throughout. Some mechanical properties show different values when measured in different directions within the same solid, and such solids are said to be anisotropic. Some properties that depends on the direction are refractive index, absorbance, electrical conductivity, resistance to shearing stress, strength of the material, etc. So a crystalline substance with a regular ordered arrangement of constituents. And suppose I measure the property, say refractive index in this direction, I will get one value. Now I am measuring the same property in another direction. So the property measured will give a different value. Crystalline substances are anisotropic, while amorphous substances are isotropic. Isotropic means same throughout. The refractive index of ordinary glass doesn't vary with the direction in which it is measured. A comparative study of the crystalline and amorphous solids are given in this table. Crystalline solid, amorphous solid. So you just pause the video and go through these properties. So far we have considered only two types of solids, crystalline solids and amorphous. But we should also consider a third type of solid which contain many randomly oriented small crystals, and these are called crystallites. So this is the crystalline substance with the ordered arrangement, and this is amorphous substance and the disordered arrangement. And in between these two is the polycrystalline solid, and it has regions where the constituents are arranged in an ordered manner. As a whole, we can consider it as amorphous. Polycrystalline solids appear to be amorphous but have microcrystalline structures, and these microcrystalline structures are called crystallites or grains. Metals often occur in polycrystalline condition. Individual crystals are randomly oriented, so a metallic sample may appear to be isotropic even though a single crystal is anisotropic. Some examples of polycrystalline solids are many metals, many ceramics, rocks, ice, etc. Malleable iron is polycrystalline, and we can see regular ordered arrangement in certain regions, and these are called grains. Polycrystalline form of silicon is used as a raw material by the solar, photovoltaic and electronic industries. Next we will study how solids are classified. By solids we mean crystalline solids. Solids are classified into four categories: molecular solids, ionic solids, metallic solids, covalent or network solids. Molecular solids are further classified as non-polar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. Let us see one by one. Non-polar molecular solids. Atoms or molecules are held by weak forces. For example, London dispersion forces, which are the weakest type of intermolecular forces. A few examples are solid hydrogen, solid chlorine, solid iodine, etc. And this is an iodine crystal. These are iodine molecules. So the force of attraction is the weak London dispersion forces. Second category is polar molecular solids. Molecules are held together by relatively strong dipole-dipole interactions, soft and non-conductors of electricity. Some examples are solid sulfur dioxide, solid ammonia, solid HCl, etc. And this is solid ammonia crystal. And the dipole-dipole interactions hold the molecules together. The third category is hydrogen bonded molecular solids. Strong hydrogen bonding binds the molecules. Non-conductors of electricity, usually volatile liquids at room temperature. An example is ice crystal, and this dotted line represents the hydrogen bonds. The second category is the ionic solids. In ionic solids, the constituents are ions. For example, sodium chloride crystal. The small balls are sodium ions and the green are chloride ions. Ions are constituent particles, and these ions are bound by Coulombic forces. They are hard and brittle, high melting and boiling points. They are insulators in solid state, but conductors in molten state and in aqueous solutions. Next is metallic solids. In metallic solids, positive ions are surrounded by a sea of free electrons. These are mobile and are evenly spread out through the crystal. The high electrical and thermal conductivity is due to free electrons. The color and luster of metal is also due to the presence of free electrons. Metals are highly malleable and ductile. For example, this crystal, and the crystal lattice contains the metal ion. The small spheres are electrons. So this is a face-centered crystal. Examples, for example, aluminum, nickel, silver, copper, etc. Next is covalent or network solids. An example is diamond. Here the white spheres are carbon atom lines on the corners as well as face centers of the crystal. The brown or red balls are carbon atoms lying on the body diagonal, and each body diagonal contains one carbon atom. There are 4 body diagonals. Another example is graphite. Graphite has a structure different from that of diamond. It has a sheet structure. So this is, we can call it as sheet A, and this is sheet B, and again this sheet A repeats. So the distance between the sheet A and B be 335 picometer. The carbon-carbon distance is 142 picometer. Each carbon atom is connected to 3 other carbon atoms through covalent bonds. Let us study more about the diamond structure. Since covalent bonds are strong and directional, the atoms are held very strongly at their positions. These solids are hard and brittle, and they have extremely high melting points and may even decompose before melting. These compounds are insulators and do not conduct electricity. For example, diamond and silicon carbide. In the diamond structure shown, atoms 2, 3, 4 and 5 makes the corners of a tetrahedron, and atom 1 lie at the middle of it. Atom 2, atom 3, atom 5, atom 4. Each carbon atom is sp3 hybridized and bonded to 4 other carbon atoms and forms a 3-dimensional structure. So even though this appears to be not connected, but all the carbon atoms are connected to 4 other carbon atoms. And these lines shows the boundary of the crystal lattice. The carbon atom 1 lie in the body diagonal of the crystal. Body diagonal is the line joining opposite corners. And there are 4 body diagonals, and on each body diagonal there will be 1 carbon atom. The second is graphite. Graphite is an exception. It is soft and conducts electricity. The exceptional properties are due to its structure. Carbon atoms are arranged in different layers, and each atom is covalently bonded to 3 of its neighboring atoms in the same layer. The carbon atoms are sp2 hybridized. The 4th valence of electron of each carbon is present between the layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide over the other. This makes graphite a good lubricant. A single layer of this structure is called graphene, which is a material with wonderful properties. It has remarkable strength, flexibility, and a high electrical and thermal conductivity. Now let us have a look at the summary sheet for the classification of solids. Types of solids, constituents, bonding type, examples, physical nature, electrical conductivity, melting point, etc. You just pause the video and go through this table. The main characteristics of crystalline solids is a regular and repeating pattern of constituent particles. For diagrammatic representation of the crystalline solids, the constituents are depicted as points. A regular three-dimensional array of such points is called a crystal lattice. Let us see how a lattice is constructed. Let me draw a transparent cube, and I am marking the center of the cube. Now I duplicate it, and one more copy. So I have a row of 3 such cubes. Now I copy that cubes once more. So I have now 3 rows of such cubes, or a 2-dimensional array of transparent cubes. The centers of all the cubes are marked. Now what I am doing is, I delete the transparent cube one by one, keeping the central point. So first one, second one, third one, etc. All the cubes are deleted. Now I got certain points. I join these points by means of straight lines. And this arrangement is a 2-dimensional lattice. Now let me construct a 3-dimensional lattice. So this is a 2-dimensional lattice of transparent cubes, and the center of each cube is marked. Now I place another cube, another 2-dimensional set of cubes above that and more above that. Now I have a 3-dimensional array of small cubes. As before, I am deleting all the cubes so that I got certain points alone. These points do not give any pattern, but now I am connecting it by means of straight lines. Now the geometrical shape of the cube is, or the points are obtained. And these are our points, and this is called a space lattice or crystal lattice. And a space lattice or a crystal lattice is 3-dimensional. Because of the regularity of the crystal structure, a constituent in a crystal can be represented by a point. An array of such points is called a lattice. If the points are arranged in 2 dimensions, it is called a 2-dimensional lattice, and if it is in 3-dimensional, it is called a 3-dimensional lattice, space lattice, or crystal lattice. An essential property of the lattice is that each point in the lattice has exactly the same environment as any other point representing the same atom, molecule, or ion. So we may think that this point is at the corner of the crystal lattice and this one at the middle. But if you extend the crystal in these directions, and this point also be same as that of the middle point, both these points will have the same environment. Lattice points are joined by straight lines to bring about the geometry of the lattice. Each point in the lattice is called a lattice point or a lattice site. Let me construct a 2-dimensional lattice by placing points in a particular regular manner and call it as lattice A. Now let me construct another 2-dimensional lattice by placing points in a regular manner but different from the first one. So in this case, points of the second row fits below the midpoint of the points of the first row. We can now construct a layer of such crystals by placing constituents at the lattice points. We imagine that the constituents to be hard spheres and are called motifs or bases for the construction. So these are the motifs, and these motifs are assumed to be hard spheres. So this is lattice A and lattice B. Each repeated motif or basis has the same structure and a spatial orientation as any other one in the crystal. By arranging points in this way, I have constructed a 2D lattice. Now, look at the colored rectangle, the corners of which touches the lattice points. Now I delete all the points in the lattice except the first four. The 2D lattice has been disappeared. Now I can reconstruct the previous lattice by the movement of the red rectangle with the 4 lattice points in 2 dimensions. So it is moving in this direction. Suppose that it places 2 lattice points here. Further moving towards right, 2 lattice points. Going down, it places 2 lattice points again. Then towards left, 1 more lattice point. Again down, 2 lattice points. 1 more lattice point. Another lattice point. Thus, the movement or translation of a basic unit in x and y directions reconstruct the previous lattice. Now look at this white rectangle. It represents the basic unit, which is moved in 2 dimensions. It is characterized by lengths a and b and angle gamma. Now I am constructing another 2D lattice by placing points in a different way. Here we can imagine basic units with different shapes. So this may be a basic unit or this may be a basic unit. The translation of these basic units in 3 dimensions can construct the whole crystal. The colored parallelograms are called 2D unit cells and a translation of which generate the crystal lattice. One condition is that every point in the crystal lattice must be exactly in the same environment as every other point in the lattice, and this imposes some restrictions in selecting the unit cell. Based on geometrical conditions, we can have only 5 different unit cells in 2 dimensions, and these are the 5 2D Bravais lattices. A 2-dimensional unit cell is the smallest portion of the 2D lattice, which when repeated in different directions generates the entire lattice. A 2D unit cell is characterized by lengths a, b and angle gamma between them. Based on geometrical conditions, we could arrange lattice points only in 5 ways in a 2D lattice. And these are the 5 2D Bravais lattices. These are the 5 2D lattice unit cells. So this distance A, B, angle gamma. Here A is not equal to B, gamma not equal to 90 degree. This unit cell is called oblique. This is A not equal to B but gamma 90 degree. And this is called a rectangular. And here there is one lattice point at the center of the unit cell. Again A not equal to B but gamma equals 90 degree and it is called a rectangular center. Here A and B are the same. Gamma 90 degree and this is called a square unit cell. And this is hexagonal. A is equal to B but gamma equals 120 degree. Only these 4 lattice points belong to the unit cell. These 3 are shown just to show the hexagonal shape. Now let us see how a 3D unit cell is identified. Here you see a 3D lattice or a crystal lattice. Consider a small shaded cube within the 3D lattice. 8 lattice points touches the cube. 1, 2, 3, 4 above and 1, 2, 3, 4 below. Forget about other lattice points and allow this base unit to move in 3 dimensions. As before, we get the whole 3D lattice. Moves towards right, then coming down, and it moves in 3 dimensions. And the movement generated the whole crystal. A small part of the space lattice is enough to specify the crystal completely. unit cell is the smallest portion of the space lattice, which when repeated continuously in different directions generate the entire lattice. The external appearance of the crystal is determined by the shape and dimension of the unit cell. And this is copper sulfide crystal. And this is the shape of the unit cell. The whole crystal has the shape of the unit cell. A unit cell is characterized by three edge lengths A, B, and C, and three angles alpha, beta, and gamma. These are called the unit cell parameters. So let this be the distance A, B, and C. So the angle between A and B is called gamma. That between A and C is called beta. And that between C and B is called alpha. Unit cell is the smallest portion of the space lattice, which when repeated continuously in 3 dimensions generate the entire lattice. Unit cells are of two types, primitive unit cell and a centered unit cell. In a primitive unit cell, the constant particles are present only on corner positions of the unit cell. In centered unit cell, one or more constant particles are present at positions other than corners, in addition to those at corners. And this is a primitive unit cell or a simple unit cell. The lattice points are only at the corners. And this one is a face-centered unit cell. So at the corners there are points. In addition to that, at the center of each face there will be a point. And this is the body-centered unit cell. In addition to corner points, one point is entirely within the unit cell. And this one is end-centered unit cell. In addition to corner points, there are 2 points at the center of opposite sides. The 7 crystal systems. The French mathematician Auguste Brave showed that there can be only 14 possible ways in which lattice points can be arranged such that each point in a crystal lattice has the same environment as every other point in the lattice. These are called 14 Brave lattices. Based on the primitive unit cell parameters and the type of unit cells, these 14 lattices can be classified into 7 crystal systems. And this table shows the 7 crystal systems. And the first one is cubic system. The edge lengths and axial angles. Edge lengths are A equal B equal C. Axial angles are alpha equal beta equal gamma equal 90 degree. So the number of Breve lattices are 3. They are primitive, body-centered, face-centered. Some examples are sodium chloride, zinc sulfide, copper metal, etc. The second crystal system is tetragonal. Here A is equal to B, but C is not equal to A and B. But alpha equal beta equal gamma equal 90 degree. And only 2 Breve lattices are possible. Examples are SnO2, titanium dioxide, TiO2, calcium sulfate, white tin, etc. Third one is orthorhombic. Here A not equal to B, not equal to C, but alpha equal beta equal gamma 90 degree. And 4 Breve lattices are possible. Primitive, body-centered, face-centered, and end-centered. Examples are rhombic sulfur, potassium nitrate, barium sulfate, magnesium sulfate, etc. Next is hexagonal. And here A is equal to B, but not equal to C. Alpha equal beta equal 90 degree, but gamma equals 120 degree. And only one Breve lattice is possible, and that is the primitive lattice. Example, graphite, zinc oxide, cadmium sulfate, SiA2, etc. Fifth one is rhombohedral. It is also known as trigonal. Here A is equal to B is equal to C, and alpha equal beta equal gamma, but they are not equal to 90 degree. Only one Bravais lattice is possible, that is the primitive one. Examples are calcite, calcium carbonate, mercuric sulfide, etc. Next one is monoclinic. Here A not equal to B not equal to C, but alpha equal gamma equal 90 degree and beta not equal to 90 degree. Two Bravais lattices are possible, primitive and end-centered. Examples are monoclinic sulfur, sodium sulfates, 10H2, etc. The last one is triclinic. Here A not equal to B not equal to C, and alpha not equal to beta not equal to gamma, and again not equal to 90 degree. Only one Bravais lattice is possible, that is primitive. Examples are potassium dichromate, copper sulfate, H3BO3, etc. So the total Bravais lattices 3 plus 2 plus 4 plus 1 plus 1 plus 2 plus 1, and this will be 14. The following diagrams show the 14 Bravais lattices. First, let us see the cubic. For cubic, A is equal to B equal to C, alpha equals beta equals gamma 90 degree. So this is the simple cubic lattice, and this one is the face-centered cubic lattice, and this is the body-centered cubic lattice. Second one is tetragonal. For tetragonal, A equal B not equal to C, but alpha equal beta equal gamma 90 degree. And this is the primitive unit cell, and this is body-centered unit cell. And here A not equal to B not equal to C, alpha equal gamma equal 90 degree, and beta not equal to 90 degree. Two unit cells are possible for monoclinic, primitive and end-centered. Next is orthorhombic. For orthorhombic, A not equal to B not equal to C, but alpha equal beta equal gamma 90 degree. And this is the primitive unit cell, and this one is the face-centered unit cell, and this is the body-centered unit cell, and this one is the end-centered unit cell. Now take triclinic, where A not equal to B not equal to C, alpha not equal to beta not equal to gamma not equal to 90 degree. Only one unit cell is possible, that is primitive. Then hexagonal, A equal to B not equal to C, alpha equal beta equal 90 degree, but gamma equals 120 degree. So this is hexagonal unit cell, and only primitive is possible. The actual unit cell is this one, that is the points which are connected by solid lines, and the dotted lines are shown to show the hexagonal shape. Then rhombohedral, here A equal B equal C, alpha equal beta equal gamma not equal to 90 degree, and only one unit cell is possible, and that is the primitive unit cell. In a lattice, the same lattice point is shared by different unit cells, so the effective number of atoms per unit cell varies. And let us take the primitive cubic lattice. So consider this red lattice point. Now this is actually the unit cell, and this red lattice point is shared by this unit cell as well as this one more. So 4 unit cell from the back. Similarly, the same unit cell will be shared by 4 from the front. So totally 8 unit cells share 1 point. So this is the unit cell, and that is the open structure. The space filling structure will be this one. Now if we take the actual unit cell, this one may be the actual unit cell, that is the actual portion of atoms belonging to one unit cell, that is the primitive cubic unit cell. So this unit cell gets only 1/8 of this corner point. So 1/8 of a corner atom. So each constituent at a corner is shared by 8 adjacent unit cells. So therefore only 1/8 of an atom, molecule or ion belong to a particular unit cell. Therefore the total number of atoms in one unit cell is 8 into 1/8. There are 8 corners, that is equal to 1 atom. Now consider the body-centered unit cell. So in addition to corner points, there is one point at the middle of the cube. So if we take the space filling structure, this one will be the space filling structure. So the actual portion of atom belonging to one unit cell will be this one. This is 1/8, another 1/8, 1/8. So this is only an imaginary figure. So these are the corner atoms. And this center atom is totally belong to the unit cell. So this unit cell get only 1/8 of a corner atom. So 8 corners are there in 1/8, that is 1 atom. The atom at the body center belongs to this unit cell only. So therefore one more atom. Hence the effective number of atoms per unit cell is 2. In face-centered cubic unit cell, there are points at the center of the faces also. And this is a space filling structure. If we take the imaginary unit cell, so these are the corner points. So a corner atom is shared by 8 unit cell. So we get only 1/8. Now an atom on the center of the face is shared by 2 unit cell. So therefore this unit cell get half of the face-centered atom. There are 8 corners, so 8 into 1/8. So we get 1 atom. Then 6 faces are there, and half from each one, so that 6 into half 3. So effective number of atoms per unit cell is 4. Now let us see the close packing of constituent in a crystal. In solids, the constituents are close packed, leaving minimum vacant space. For simplicity, we assume the constituent particles as identical hard spheres. We build a three-dimensional structure in 3 steps based on this assumption. The first step is a close packing of one dimension. The spheres are arranged in a row touching each other. There is only one way to arrange spheres in this manner. In this case, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is the coordination number. Thus, in a one-dimensional close-packed arrangement, the coordination number is 2. The second step is making close packing in 2 dimensions, and this can be done in 2 ways. In one case, the second row may be placed in contact with the first such that the spheres of the second row are exactly below that of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A type, the second row is also A type. We place more rows to obtain A type arrangement. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the 2-dimensional coordination number is 4. The corners of the red square touches the center of the neighboring 4 spheres. Hence, this packing is called a square close packing in 2 dimensions. In another type of arrangement, the second row may be placed below the first in a staggered manner such that the spheres of the second row fit in the depressions of the first row. If the spheres in first row are called A type, those in second row are different and may be called B type. When a third row comes, it is placed just adjacent to the second row in a staggered manner and its spheres are aligned with those of the first layer. Hence that also is an A-type layer. The fourth row will be aligned to the second row. Hence this arrangement will be AB type. Here each sphere is in contact with 6 of its neighbors. So this sphere touches 6 of its neighbors. So the coordination number is 6. And this type of close packing is hexagonal close packing. Now let us consider the close packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. We can have 3-dimensional structures from 2-dimensional square close packed structures and also from 2-dimensional hexagonal close packed structures. First, let us see how 3D structures are obtained from 2D square close packing structures. So this is a 2D square close packed structure or one layer of atoms. Now I am placing another layer in front of it. One more and one more. Or we can consider it as this is the bottom layer and we are placing other layers above that or stacking the layers. And here each layer is same as the other one. So we can have an AA type arrangement. If we connect the centers of 8 spheres, we get a cube. And here the coordination number is 6. So consider this atom in this layer. Below that one more is there and one atom touches from the back layer, and if you place one layer in front of it and one atom touches this one. So totally 4 plus 2, the coordination number is 6. And no non-natural crystals exist in simple cubic close packing because a large vacant space is there in this case. One more type of close packing is possible with the 2D square close packed layers. And let us see how. The second layer is placed in the depressions of the first layer and so on. So this is the first layer. Now the second layer atoms come placed in the depressions of the first one. Therefore it forms an AB type pattern. So 4 atoms of the first layer, 1 atom of the second layer and 4 atoms of the third layer. And this is called a body-centered cubic close packing or BCC. Now the central atom touches 8 other atoms, 4 from above and 4 below. So therefore in this case the coordination number is 8. Examples: metals like lithium, sodium, potassium, rubidium and cesium crystallizes in body-centered cubic close packing structure. Now let us consider 3-dimensional close packing structures from 2-dimensional hexagonal close packed layers. So there are 2 ways in placing the second layer. So this is the hexagonal close packed layer. That is the first layer. These are the triangular voids. So all these are triangular voids. So the second layer atoms, that is yellow atoms, go to the triangular voids. So this is one triangular void, and if you consider one atom of the second one, so this triangular void is covered by this second layer atom and it forms a void, and that void is called a tetrahedral void. Now This is the triangular void. Now the triangular void of the second layer may be arranged in another manner. And a void is generated in between these 6 atoms, and this void is known as octahedral void. So there may be tetrahedral voids as well as octahedral voids. These are tetrahedral voids. On the other hand, these open voids are octahedral voids. Now let us see how these tetrahedral and octahedral voids are ascertained. So consider one sphere, second, and 3 spheres of one layer. So we are considering only the first layer and only 3 atoms from the first layer, and they form a triangular void. Now consider the second layer. Here we are considering only one sphere from the second layer. So if you connect the centers of these 4 spheres, you will get a tetrahedron. And such a void is known as a tetrahedral void. Now let us consider 3 atoms of the first layer. And we are considering again 3 atoms from the second layer. They come in a staggered manner. So when we place it like this, we get a structure. And inside that there will be a void. Now connect this atom with these 4 atoms. And suppose that I turn this figure in this direction so that the yellow sphere goes to the back side of the structure. Now mark like this. Now I am connecting these 2 structures. This is the upper structure and this one is the bottom structure. And when you connect these 2, you get a octahedron. And in the case of close packed structures, if the total number of close packed structures or spheres are n, then the number of tetrahedral voids found will be 2n. And the number of octahedral voids will be n. So the number of tetrahedral voids will be double the number of octahedral voids, and octahedral voids will be equal to the number of spheres that make the structure. Now we can place a third layer, and a third layer can be placed in 2 ways. One, covering the tetrahedral void. So let this be a hexagonal 2D layer, and only 7 atoms are shown here. Now above that, this is the second layer, and now the third layer is placed in such a way that the second layer, when combined with the middle atom, it forms a tetrahedral void. Now we place the third layer in such a way that the middle atom of the third layer will cover this tetrahedral void, and this tetrahedral void is open in this direction. Here it is closed. So therefore we can place a third layer in such a manner that it covers the tetrahedral voids. So we can say that this is the first layer, A layer, and a B layer is different from that, but the third layer is a repetition of the first layer, and we can call it as an AB-AB pattern. And this type of close packing is known as hexagonal close packing. Now second method is covering the octahedral voids. So we have one layer. Now this is the second layer that is different from the first layer, and the third layer also is different. So these 3 green spheres and 3 pink spheres form an octahedral void. These 6 atoms form an octahedral void, and in this direction that octahedral void is closed. So this atom closes the octahedral void, but at the top it is open. Now we place the fourth layer, and a fourth layer is a repetition of the first one. So we call this as A layer, B layer, C layer, and again a layer. And such a close packing is called a cubic close packing. So two types of close packing we can have by placing a third layer over the second layer. One is hexagonal close packing, AB pattern, and a cubic close packing, ABC pattern. Now we can see an animation. So this is the first layer, and that is the second layer. We can call it as B layer, and the third layer. So every third layer is a repetition of the first one, and every fourth will be a repetition of the second one. And here the pattern is AB, and this is the hexagonal close packing or HCP. Now consider the cubic close packing covering octahedral, and this is the first layer, second layer that is different from first, third layer that also is different from the second, and the fourth layer repeats. The fourth layer is a repetition of the first one, and here the pattern is ABC, and such an arrangement is called cubic close packing, CCP. Examples of hexagonal close packing are zinc, magnesium, cadmium, etc. forms HCP, while copper, silver, gold, etc. forms CCP. It can be shown that the coordination number in both these type of close packing is 12. So let this be hexagonal close packing AB, and I am showing only 3 layers, that is B layer, A layer, and another B layer. Now this is the central atom of the A layer. When the B layer comes close here, it will touch these 3 holes. Similarly, when this layer come here, and this central atom will be in touch with these 3 holes. So the central atom touches 3 from above and 3 from below. And the same layer it touches 6 other atoms or spheres. So 6 here, 3 from here, 3 from here. So a total of 12 atoms. Now the cubic close packing, and here it is, the pattern is ABC. So a C layer, then comes an A layer, then comes the B layer. And now we take the middle of this sphere of the A layer, it touches these 3 of the C layer and 3 of the B layer. And within the layer there are 6. So 6 plus 6, 12. The cubic close packed structure generates a face-centered cubic lattice. And it is slightly confusing, but the following animation will make it clear. Here we have the first layer, that is A layer, B layer, C layer, and again A layer. So this is a cubic close packing, ABC pattern. And 1 atom each from A layer, 6 atoms from B, and also 6 atoms, 1 in the other side, 6 atoms from C layer, and a total number of atoms is 14. And now what I am going to do is I am turning it in this direction, rotating this structure about 135 degrees in this direction. And now let us see what happens. So it changes like this. So this A layer comes here and this A layer goes here. Now connect the centers of these atoms. And now this green atom is at the center of this face. And this is a face-centered cubic unit cell. And this is the A layer, and this is the B layer, and this one is the C layer, and again the A layer. So it shows that a cubic close packing is same as the face-centered cubic unit cell. Let us work out some multiple choice questions related to what we have studied so far. Question 1. The binding force or forces operating in molecular solid is or are 1. Water Walls forces, 2. Hydrogen bond, 3. London forces, 4. All the above. So in molecular solids, all these forces are operating. So answer is 4. Which of the following is not a network solid? 1. SiO2, 2. SiC, 3. Aluminum nitride ALN, 4. H2O. So SiO2, SiC, silicon carbide and aluminum nitride all are network solids. And H2O is hydrogen bonded. So the answer is option 4. When constant particles are present only at the corners of a unit cell, it is called 1. Primitive, 2. Body-centered, 3. Face-centered, 4. End-centered. So when constituents are present only at the corners of the unit cell, it is called a primitive. Question 4. Which of the following crystal systems has the edge length parameters as A not equal to B, not equal to C, and angle parameters as alpha not equal to beta, not equal to gamma, not equal to 90 degree? Option 1 tetragonal, option 2 trigonal, triclinic, and option 4 monoclinic. Let us check the crystal systems. A not equal to B, not equal to C, and alpha not equal to beta, not equal to gamma, and a not equal to 90 degree. And this system is triclinic. So option 3 is the correct answer. Question 5. ABC pattern of arrangement of constituent is found in the following type of close packing. 1. Simple cubic close packing, hexagonal cubic close packing, body-centered cubic close packing, 4. Cubic close packing. So ABC pattern is observed in cubic close packing. The number of tetrahedral and octahedral voids in a CCP array of 100 atoms are respectively 200 and 100, 100 and 200, 200 and 200, 100 and 100. Number of octahedral voids will be same as the number of atoms from the lattice, and a tetrahedral will be double the number of atoms forming the lattice. So therefore there are 100 atoms. So octahedral voids will be 100 and a tetrahedral will be 200. So option 1 is the correct answer. Choose the incorrect statement. Both the diamond and graphite are used as dry lubricants. Both the diamond and graphite have two-dimensional network. In diamond, carbon is sp3 hybridized, while in graphite it is sp2 hybridized. Diamond is covalent, while graphite is ionic. So in diamond, we have to choose the correct statement. In diamond, carbon is sp3 hybridized, while in graphite it is sp2 hybridized. Option 3 is the correct answer. Choose the incorrect statement. 1. Crystalline substances are anisotropic, while amorphous substances are isotropic. Crystalline substances are isotropic, while amorphous substances are anisotropic. Ordinary glass is an amorphous substance. Refractive index of crystalline substance depend on the direction in which it is measured. We know that crystalline substances are anisotropic while amorphous substances are isotropic. So this is a correct statement. We have to choose the incorrect one. So crystalline substances are isotropic while amorphous substances are anisotropic. That is an incorrect statement. The other two are correct statements. So answer is option 2. The number of Bravais lattices for monoclinic crystal and its dimensions are 1, 2. These are the dimensions. 2, 4, 3, option 3, 2, and option 4. We have to consider monoclinic system. These are the 7 crystal systems in which the monoclinic A not equal to B not equal to C, alpha equal gamma equal 90 degree, beta not equal to 90 degree, and the number of Bravais lattices is 2. Therefore, the correct option is option 3. Graphite is a good conductor of electricity due to the presence of 1 lone pair of electrons, 3 valence electrons, 3 cations, 4 anions. So in graphite, carbon atoms are sp2 hybridized and the 4th valence electron is free. Question 11. The cubic close packing arrangement generates dash lattice. Simple cubic lattice, body-centered cubic lattice, face-centered cubic lattice, and a hexagonal lattice. So CCP is same as cubic close packed lattice. So option 3 is correct. In HCP arrangement, the coordination number of an atom will be 8, 6, 4, 12. And we have seen that in both HCP and CCP, the coordination number is 12. In solid state part 2, we will learn about the following topics: how to locate tetrahedral and octahedral voids, packing efficiency in different types of close packed structures, determination of the formula of compounds, ionic solids, determination of density of a crystal, multiple choice questions, and paragraph type questions. The link for part 2 is given in the description of this video.